Hello.
Hey, Dr. Hayden, how's it going?
Pretty well, thanks. How about you?
Yeah, I'm liking the sunshine.
Yes, that is definitely an improvement.
Yeah,
Keeps teasing us. Excuse me, I have to go yell at a dog.
sure.
Panzer, be quiet. Okay. So I guess, okay, you've got a third person here. I have to go find, I just got out of class, so I have to go find those sheets.
Hello.
Hey, how's it going?
Good. How are you?
Good,
Hi.
good.
Hi.
I don't think I've met you, Masood. I'm Pat Hayden.
Yeah, I'm Masood. Nice to meet you. Yeah, I'm
Nice to
PhD
meet you.
in material science and engineering. So,
Okay. You said you just joined here?
no, I started my second year actually. Yeah.
Oh, okay. All right. Well, welcome to Michigan. I don't know if you came from downstate or not, but welcome to the UP anyway.
Yeah, I came from Iran actually.
Oh, directly from Iran?
Yeah.
Oh, wow. Well, welcome to the US then.
Thank you.
How in the world did you land an interview from Iran to here?
Actually, it wasn't my fault. Actually, it was my wife's fault. Yeah, she actually got the position here in material science department, and then when we arrived, yeah, I decided to pursue my PhD here as well.
Well, double welcome then. All right, anyway, I got to go find those sheets or I can't. I think it's not the rubric. What did they call those things? I could probably on Word. I have to find it. File open recent. I should be able to find it there. All right. All right. Well, I don't want to hold anybody up. I'll just take notes and I'll find those sheets somewhere. And oh, I guess I still have a minute, maybe. Oh, maybe not.
I think we have just a minute.
Okay. Where? I sworn I downloaded those to save, but.
We are actually waiting on one more contestant who is part of this presentation. So,
Oh, okay. All right, good. Then I'll just keep looking. I think I'm going to have to go all the way back to find that email.
Sarvata, I see the recording is going right now because I see the option to pause or stop recording, but I can't figure out how to record locally while the cloud recording is also going on.
It's something you just leave it on. I think it should be okay. We can edit that piece out and it should directly go in the cloud.
Okay, sounds good. Okay, well, it's 1 o'clock and we have both our judges and presenters here. My name is Alexander Apostle. I'm a PhD student in Department of Chemistry, but I'm just the moderator for this session. So we can get started. I just wanted to give a little welcome and just thank everybody for coming out and taking part in this year's graduate research colloquium. So I'm the moderator. Just to lay down a couple ground rules before we start, each contestant will have about 12 minutes to present. I shouldn't say about, they have 12 minutes to present maximum. Your time will start the second you start speaking. So I'll start the timer and I will give you 1 minute warning by unfortunately interrupting you if you're talking. So I kind of just have to blurt out and just say 1 minute. Sorry, I don't mean to interrupt anybody, but So once you're ready to start, just give me a verbal cue. You can just say start, just so I know when exactly to start it and just be most fair. Also, because this is a virtual format, I'm gonna have to advance through your slides. So please just say next or next slide, and I'll go to the next slide. And we just have to do it that way. I'm gonna have to share my screen, and I have your slides on here. So I'll introduce everybody before we go. And we can jump right into the presentations need be. At the end of the presentation, judges can unmute themselves and ask questions to the participants for about 5 minutes. And while the judges are scoring, I'll moderate questions from the general audience. I ask the audience to stay muted during the presentation and drop their questions in the chat box during or after the presentation. So just to introduce our judges, we have Dr. Patricia Hayden and Dr. Deborah Charlesworth. And I'll share my screen here. Our first presenter is so hold on, I gotta get my timer ready before I jump to the next slide. Okay. All right. So our first presenter is Masoud Krasai, and he is going to be presenting on mechanical and electrical characteristics of.
Alexander, can I just interrupt? Can
Yeah,
you
what's up?
switch on to a full slideshow mode? We can still see it in
Oh,
the
sorry.
present-
Thanks for saying that.
Mhm.
This thing's in the way.
You should find it in the home menu on the right-hand side bottom of the screen. So there is a small icon. On the right
Oh,
side. Yeah.
No.
no.
Yes.
Oh, hey. All right. Thank you. All right. So Masoud is going to be presenting on mechanical and electrical characteristics of additively manufactured conductive epoxy carbon nanotube composites. He is in the PhD Material Sciences and Engineering program, and you may start whenever you're ready.
Yeah, thanks for the introduction. Hello, everyone. I'm glad to start my presentation for GRC 2021. Next, please. So the goal of our research is develop new knowledge that will help us to create 3D printed epoxy structure, which are electrical conductive and has excellent mechanical properties and has the application in different fields like aerospace structural part, electromagnetic shielding, and electronic packaging. Next, please. So why we choose epoxy? Because when we add 45% carbon fiber to the epoxy, we are going to have the same strength as a steel part with 80% weight reduction. And when you add 20% carbon fiber to the epoxy, you're going to have the same strength as aluminum part. In this case, we have 40% weight reduction. Next, please. So when we want to talk about the additive manufacturing of polymer composite, we have two different categories, thermoplastics and thermosets. Thermoplastics like ABS, PLA, PETG, and the method in order to print them is the fused filament fabrication. Next, please. In order to do that, we have to have prepare a filament. We have to mix our thermoplastic with some fuel like chopped polymer, glass, or carbon fiber. When we fabricate the filament, we have to melt it, extrude it, and after extrusion, we're going to have the parts that we want. So what is the problem in here? Next, please. The problem is the strength of the thermoplastics are very low and it's lower than what we expected. Next, please. So what is the reason of that? The reason is due to the porosity between the print lines in this method and the poor interfacial adhesion between the fibers and matrix. Next, please. As you can see in these SEM images, the porosity and distance and voids between the print lines and each individual lines are totally unavoidable because of the nature of this method. So what we recommend, next please. So we recommend using thermosets like epoxy resin. And in order to do that, we have to and 3D print with direct ink printing, and we're going to need the printable ink with epoxy. After printing, then we cure the sample, and after curing, we don't have that space or voids between the layers and between each individual lines. So what is the problem here? The problem is the printability of the epoxy. So as we all know, the epoxy are not printable, and they are so liquidy. Next, please. So in this research, we used EPON 826. Carbon fiber is traditionally used for increasing the strength of material, and we also use that in this research. Nanoclay recently used for as a rheological modifier in order to increase the viscosity and also storage and loss modulus of the ink in order to print the material. So CNT carbon nanotubes also has the excellent mechanical and electrical properties, which is totally common in order to increase the strength and add the electrical conductivity to the epoxy. Next, please. So as I already mentioned, we have EPON 826, multi-wall carbon nanotubes, carbon fibers, nanoclay, and curing agent. Next, please. So the ink preparation is we mix the epoxy with the acetone solvent, then we add the carbon nanotubes, we sonicate that for 30 minutes, and after 2 hours of mixing with the magnetic ester, then the acetone will be evaporated by increasing the temperature to 85 degrees. And after that, we add carbon fiber, curing agent, nanoclay using the centrifugal thinking mixer. So the thinking mixer is the mixer that has a rotational speed of 800 RPM. So it rotates at this direction, and also has a centrifugal speed or rotational speed of 2000 RPM in this direction. So it's going to give us a better dispersion of material. After that, next please. After that, we fill this ink into the 10 ml syringes, and we print it with 510 micron diameter of nozzle tips. The printing speed was 15 millimeter per second. Next, please. And after printing, we're going to cure the sample at 100 degrees for 15 hours and 220 for 2 hours. Next, please. So for the dispersion of the carbon nanotubes and carbon fiber, as you can see into the image, the second image from left. So we had some agglomeration of CNTs into the epoxy after sonication and using the magnetic strip. But when we add nanoclay, carbon fiber, and everything with a thinking mixer, with using the thinking mixer, we didn't observe any kind of agglomeration into the epoxy. Next, please. So we were able to produce some printable ink with and without nanoclay. By having 10 parts per 100 nanoclay, we were able to print composition from 0 to 1 part per 100 CNTs. So, but for the 2 parts per 100 CNT and having 10 parts per 100 nanoclay, the pressure that the material needs to be extruded through the nozzle was exceeded to the amount that brings so many challenges, like clogging of nozzle and etc. So we were not able to print the material by having 10 parts per 100 nanoclay and 2 parts per 100 CNT. But when we remove the nanoclay from the composition and we increase the CNT concentration, we were able to print the material, the composition, the composites with 2 parts per 100 carbon nanotubes. And the pressure that it needs was 50 psi. Next, please. So in order to evaluate the rheological properties of that, as you can see in the left image, the epoxy and the pure epoxy, which is shown by the brown color, as you can see, the loss modulus is higher than the storage modulus. It means that pure epoxy acts as a liquid material. But when we add nanoparticle like nanoclay, CNT, and carbon fiber also, as you can see, next please, there's a certain point that it shows the shear yield point. Before that, the storage modulus is higher than loss modulus, and after that, the loss modulus became higher than storage modulus. It means that at this point, the material changed from the solid behavior to the liquid behavior, and that is a very important point for us, because this is the point that we are able to extrude the material through the nozzle, and after printing, because we remove the shear stress, the material has the ability to maintain the shape after printing, so we are able to print the material. As you can see in the right figure, next please, by increasing the shear rate, the viscosity decrease for the printable inks, not for the pure epoxy at the bottom. So, and we call this shear thin behavior of the inks, and that's very important and crucial for the 3D printing, because we want to have something that by increasing the shear rate through the nozzle, the viscosity decrease. So next, please. After that, after the printing and curing, we evaluate the tensile properties of the material. So as you can see in the left image, the tensile strength increased from the pure samples that we cast for the pure epoxy to the that is the tensile strength in this case is about 35 megapascal to 90 megapascal. So it's not because of the adding 2 parts per 100 carbon nanotubes and 10 parts per 100 carbon fiber. It's also because we remove the nanoclay, which is the brittle part in this case from the composition. And also the tensile modulus increased from about 3 to 10 gigapascal. Next, please. For the flexure strength also, because of the involvement of compression stress in this test, when we have more and more fillers into the material, we have more flexure strength. As you can see, for the pure epoxy, the flexure strength was about 50 megapascal, but for the composition that contains 0.5 per 100 carbon nanotubes and 10 part per 100 carbon fiber, and also nanoclay, it is about 150 megapascal. Also, the flexure modulus increased from about 2 to about 7 gigapascal. Next, please. So if we want to characterize the fracture surface of the materials for the neat epoxy that we cast the sample, the smooth surface indicate that we have the brittle fracture. So it's very brittle material, the neat epoxy that we cast. Next, please. So by adding for example, carbon nanotubes, you can see the bridging effect between the crack, between the two sides of crack, that will help to increase the strength of the material. Next, please. Also, we had some breakage of fillers of carbon fiber and carbon nanotubes at the fracture surfaces. So it indicates that the fracture mechanism is because of the fracture of this filler. Next, please. Also, we're going to have the alignment of carbon fiber because we have the shear stress into the nozzle. We're going to have the alignment of carbon fiber during the printing direction, then the tensile strength increase. Next, please. And also for the electrical conductivity, we have the maximum for the composition that has no nanoclay, and the electrical conductivity was about 0.03 Siemens per centimeter, which is 4 orders of magnitude more than other composition. Next, please. For the conclusion, the results introduced carbon nanotubes as a rheological modifier. Adding CNT and carbon fiber increase the viscosity and storage and loss modulus, and also improve the flexure strength and tensile strength by 2.5 2.7 fold. Also, the maximum electroconductivity was about 0.03 Siemens per centimeter, which is very high for the epoxy composite. And also, the results show the potential of nanocomposite to use for aerospace and anti-static application. Next, please. Thank you very much. I'm glad to take any question.
Yep, that's 12 minutes right there. Great. Thanks for that presentation. I just want to open the floor now to the judges for 5 minutes, about 5 minutes. If you want to unmute yourselves and ask questions.
Well, I have some questions. Who's the other judge?
The other judge is Dr. Deborah Charlesworth.
It's Deb.
Hi.
I'll defer to you, Pat. You can go first.
Okay. Well, it was really interesting work. I love those images. Your SEMs were quite nice.
Thank you.
I have a couple of questions. The simplest one is, what was the surface of your carbon nanotubes? Were they functionalized in any way?
No, not at all. Actually, we are thinking about functionalizing them and having the better dispersion into the epoxy. Yeah, we are working on it.
Yeah, it would definitely give you better adhesion to the epoxy.
Yeah.
I'm not sure what all functionalities are commercially available, but I know acids are. Amines maybe not. But they're probably available, but they may be a little bit more unstable. And what was your curing agent? I take it that was an amine as well?
It is the DMEA, which is a liquid solution. So
An amine. I think that's an amine, isn't it?
yes, I think so.
Yeah. Okay. All right. So then the maybe more subjective one was, I didn't actually see a lot of analysis of the cause and effect. So you had those different impacts of properties on properties, and you did correlate them to, well, here I took the clay out there, the quantity of materials, of additives, but for the specific cause and effect, can you relate those property effects to whatever those additives were doing, other than obviously the viscosity impact? Like when you saw increases in flexural modulus or flexural strength, which species was causing what? And why?
Yeah, actually, because the nanoclay increase the viscosity, and it causes some defects and void into the material. So it will somehow we are going to have more defects into the material if we have the nanoclay. But obviously, the carbon fiber and CNT will increase the electrical conductivity and strength of the material. So, but in this case, we wanted to show also with having these fillers, also we just wanted to add that additive manufacturing by itself, because we have the alignment of carbon fiber and CNT into the composites after 3D printing. So we just wanted to add, so these filler will increase the strength and electroconductivity, but also the 3D printing by itself also can help the to have better properties.
Well, I mean, like, for example, one thing I would guess is that, especially when you have the carbon nanotubes aligned, the properties in one direction might be different from properties in another direction.
Exactly.
And I guess, I mean, obviously, you know, this is research, you can't do everything at once, but I guess I would have liked to have seen some additional discussion of the actual mechanism of interactions that led to the mechanical effects. Now, you did have that one SEM where you mentioned the bridging effect, which, but I guess I would have liked to see in a publication, I'd like to see a lot more of, you know, the whys of those things. But this was really quite nice work. Oh, one last question. So for these being inks, what is your application? What is your intended application with the aerospace?
So actually anti-static coating and also electromagnetic shielding. Material.
Okay. All right. Got it. Okay. All right. Thank you.
You're welcome. Thank you.
Hi, Masood. Nice work.
Thank you.
My question, I was wondering, you're putting in about 2% carbon nanotubes. What kind of is your goal, or how does that compare to what other people are able to do with this method? Or, 'cause I know there's often a limit with how much particles you can put into these materials, and sort of where are you aiming to be and how far off are you, and where does this compare to the literature?
Yeah, sorry, if you can go to the next slide. Next, no, just next. Yes. So I had 2 parts per 100 carbon nanotubes, and it is about 1 volume % of this material. So
Okay.
We can increase it to even 5 or 10, but then the viscosity will be very high, and we cannot 3D print that. But even with this amount of CNT and carbon fibers, we were able to print that, and we just we just saw good material properties of that. So for the normal clay, I think the maximum amount that I saw is about 15 part per 100. But for the CNT, I think we can increase it. But I've never seen any publication that add CNT as a real logical modifier in order to 3D print something again.
Okay, cool. And what statistical method did you use when you were looking at the differences between your different groups?
Yeah, t-test method.
For more than 2 groups?
Yeah, for each of the each individual
Okay.
one.
All right, thank you.
Thank you so much.
Okay, great. Thank you. Thank you, Masood. That was great. So I want to just set up my timer. So the next talk is by Nikhil Matal. The title of this talk is Myosin Independent Mechano Transmission for Sensing Stiffness of Extracellular Matrix. And Nikhil is in the the biomedical engineering PhD program. And you may begin whenever you are ready.
Okay, thank you for the introduction. It is my great honor to present my research here in GRC. So I'm ready to go. Okay, so next please. Most cells in our body need to attach to a solid environment called extracellular matrix, in ECM in short, for their survival. It supports the cell not only chemically but also mechanically. In recent 20 years, it has been revealed that the stiffness of this ECM is critical for various regulation of various cellular activities such as wound healing, tissue development, and even malignant cancer transformation. Next, please. It also affects the stem cells and its differentiation into different lineages. Therefore, how the cells feel the ECM mechanics has long been a question of interest for the mechanobiologists. Next, please. So how the cells sense and respond to the ECM stiffness. To sense the stiffness of the ECM matrix, cells have to generate and transmit mechanical force. Next, please. The process starts with the transmission of the mechanical force, which is applied either externally from the ECM or internally from the ectomycin through additions called mechanotransmission. Next, please. Yeah. And then this addition, and then this tension on the addition leads to the changes in the shape of the adapter proteins within the additions called the mechanosensation. Next, please. As you can see here in the green, the structure of the protein changes when the force comes in. Next, please. These force induced by biochemical signals causes cellular responses, resulting in the physiological behaviors such as gene expression, adhesion growth, actin bundling, etc., called mechanoresponse. But the next question, next please. But the next question arises is how exactly is this force transmitted? An understanding of this process can help in identifying treatments for the developmental disorders and cancer, as well as developing functional tissue scaffold for tissue transplantations. Next, please. The transmission of the force occurs through a sensor complex called integrant-based focal adhesion, where the cell directly contacts with this ECM. Cells apply traction. Next, please. Cells apply traction force from their cytoskeleton to the ECM through these integrant-based adhesions and get the force feedback adjusted by the ECM stiffness, also via these focal adhesions, as you can see here, this inside out and outside in force feedback loop. Next, please. So focal adhesions are basically an aggregate of more than 100 molecules, and each molecule in the structure has a distinct role in signaling, transduction, and actin regulating activities. Next, please. So there have been many studies about this big focal adhesions, which have specifically focused on establishing force versus stiffness relation. Next, please. Most of these, all of these studies have done on fibroblasts and endothelial cells have shown that an increasing force trend in response to an increasing substrate stiffness. Next, please. So yeah, next, please. One more. Yeah. So this means that there is differential transmission, differential force transmission going on with the varying stiffness. Next, please. To explain this phenomena, a force versus stiffness relationship, a molecular clutch model has been developed. In this model, next please, actin flows in a retrograde manner, mainly due to the pulling force of a motor protein, non-muscle myosin. Next please. The myosin motors pulls on the actin filaments, as you can see here, which are connected to the ECM through several parallel clutches formed by the adapted proteins, as example, talin, integrins, and fibronectin. Next, please. Once actin dynamically clutches to the cell ECM adhesion, fiber contraction deforms the substrate, resulting in the progressive force loading. This force loading leads to either clutch unbinding or talin unfolding. In the stiffer substrate, talin's unfolding rate becomes fast enough that it overcomes the unbinding time of the integrant from the ECM, thus transmitting more traction force. Next, please. However, this model heavily depends on the myosin's activity as a source of this actin retrograde flow. Next, please. In recent studies, such as this one by Zhao et al., they have been able to show that cells, even in the absence of myosin activity, are able to transmit small but significant traction force. Next, please. Next, please. Therefore, our research question is focused on whether this differential force transmission even possible when the actin is not pulling when the myosin is not pulling this actin. Next, please. So to test this hypothesis, we used a soft elastic gel as an extracellular matrix coated with fluorescent beads on the top to quantify the deformation caused by the cells, as you can see in this diagram. The cells are then imaged. Next, please. Using the total internal reflection microscopy. After imaging, the cells are detached from the surface to see the original relaxed location of the beads. Next, please. Yeah, next, please. Next, please. Next. Yeah, then these images are processed using our inbuilt MATLAB-based DFM software. Next, please. The displacement is then measured by tracking each bead using particle tracking velocimetry and corrected using outlier filtering. Next, please. Then the force maps are produced by solving the inverse problem using a regularized Fourier transform traction cytometry. Next, please. The levels of this force is then quantified using these force maps and compared among the cells on different stiffnesses. This whole technique is called the traction force microscopy. Next, please. So first we assessed how the traction in the control cells behave in response to the different gel stiffnesses. For our experiments, we used stably expressing Paxillin mRuby 3D3 fibroblast cells. As expected, next please. As expected, the total force increased with gel stiffness, as we can see here in the force maps. Next, please. After quantifying the results from these force maps, specifically a linear increase was observed up to the 5 kilopascal. Next, please. after which the total force plateaued at a stiffer regime, which is an observation. Next, please, with the previous studies. Yeah, next, please. Next, to see the effect of myosin, we treated ourselves with a myosin inhibitor, blebbistatin, to observe the traction trend independent of myosin activity. Next, please. The force map showed that the overall magnitude of the traction force reduced, but still a non-zero traction concentrated near the cell edges was still present. Furthermore, the differential force transmission was still observed. Next, please. This suggested that the differential traction against the varying stiffness is myosin independent. Next, please. So the next question arises, so where is this traction exactly coming from, if not from the myosin? So there is another source of this actin flow, which is actin polymerization. Actin filaments rapidly polymerizes at the leading edge by self-assembling at the barbed end of the filamentous actin, pushing the membrane. The actin network is pushed by the cell membrane. This continuous centripetal movement of the cell peripheral actin network creates the retrograde flow. Next, please. Yeah, here you can see the flow of the actin at the actin retrograde flow at the corners. Next, please. So next, please. So there are two main actin nucleators involved in this actin polymerization process. One is the ARP3, which is responsible for the branched actin polymerization, while another one is formin, which polymerizes actin linearly. Next, please. Yeah, next, please. Therefore, we hypothesize that this myosin-independent traction comes from actin polymerization-driven retrograde flow and its two main mediators, ARP3 and formin, which regulates the force transmission in a distinct manner. Next, please. To work on this hypothesis, we first inhibited the actin nucleator formin in addition to the myosin via formin inhibitors MIFH2 and blebbistatin, respectively. To our surprise, next, please. Yeah, next, please. To our surprise, this increasing trend was no more there, and instead, a biphasic trend of force against the stiffness was observed with the lower traction at the intermediate to the higher stiffness. Next, please. One more time. Thank you. Next, we inhibited the actin nucleator ARP3 in addition to the myosin via ARP3 inhibitor CK666 and blebbistatin, respectively. Next, please. In this case as well, cells showed a biphasic behavior in traction with the peak at intermediate stiffness. Next, please. As you can see in the graph, it peaks at around 1.5, and then after which the traction dropped with the higher stiffnesses. Next, please. Next, please. Yeah. So in conclusion, here we can say that our cells show a differential force transmission even without the myosin activity. Next, please. Both the SMIF-H2 and CK666 inhibitions resulted in the hampered force transmission at the stiffer regimes. Next, please. While the ARP3 inhibition frustrated the force transmission further than the formin inhibition at higher stiffnesses. Next, please. The frustration point comes much earlier at the softer regime for the formin inhibited cells particularly. So altogether, this work demonstrates the importance of actin polymerization's active role in the stiffness sensing. Next, please. Next, I want to discuss a little bit about the possible explanation for this ARP3 and formin behavior. Next, please. We speculate that this traction behavior might be due to small we saw some behavior at the softer regimes. We think that this might be due to small but significant clutching actin flow by the actin polymerization promoted by the other actin nucleators. Next, please. We further hypothesized that this ARP3 mediated actin flow might be slower.
1 minute.
Thank you. Than the one by formin, which can be more stickier and clutch better for traction transmission. While the formin-mediated actin assembly can confer fast enough actin flow, but it can be slipped when not assisted by the ARP3, resulting in less force transmission. Next, please. Yeah, next, please. Next, please. Yeah, so we are also working on modifying this molecular clutch model that can explain actin mechanosensitivity better. Next, please. We have introduced two new parameters, V-actin, which is the velocity of actin, and D-actin, which is the density of the actin. Next, please. With the intact ARP3, we think that additions are more of a catch point, while with the innovation of the ARP3, the additions become more of a slip bond. Next, please. So next, please. So our future endeavor involves studying the actin flow using the actin speckle microscopy with the QSM and to study this V actin at every condition. Altogether, my work will elucidate the fundamental mechanism behind the adherent cell stiffness.
That's 12
sensing.
minutes.
Thank you.
Okay, great. Thank you, Nikhil. Questions? Yeah, so again, 5 minutes for the judges to ask questions.
Well, I will defer to Deb on this one.
I'm the polymer person. So what was the most challenging part of this project and how did you overcome that challenge?
So the most difficult part was to actually manufacture these gels, which have like exact stiffnesses, and to study the adhesions, especially like the adhesions are really small, and to in the presence of masin, there are like really smaller adhesions, like nascent adhesions, and to drag force out of it is really small because there's very little deformation in the gel goes on. So I think that was the most challenging part. It was get much easier because of the software our professor developed in our lab. So yeah, but I think that's the most challenging part to take out that small force levels from the masin inhibited cells.
How were you measuring those force levels? I didn't quite understand that piece of it.
Okay, so what we do is we have these gels, soft elastic gels. We put our cells on top of it, and then we image them along with the beads, and then we remove the cells, and we then get like another bead images, which are like the reference images. So now we have two set of images, one with the beads that are displaced by the cells, and another one which are kind of relaxed bead in the original position of the beads. When we compare these, we calculate the displacement out of these images, and we produce a displacement map. After producing the displacement map using the inverse problem, we produce the force maps. And from these force maps, we then calculate how much force is actually being put into there. So that's how we do this whole process.
So the gel has a certain stiffness, it's moved a certain amount. So then you
Yes.
know you're in the linear region of that and you calculate the force roughly.
Yeah.
I'm sure there's a little more to it than that.
Yeah.
Okay. And how many samples were you doing? So I noticed there were some error bars on there. So you did this multiple times?
Yeah, so for each condition, we have like the 5 stiffnesses, and for every 5 stiffness, I have around like more than 30 cells per condition, per stiffness. Yeah.
Great, thank you.
Yeah, I'd like to continue along that theme because I was curious about those effects as well. So how big are the gels that you're measuring? I mean, what are their dimensions?
So the gels are around 45 microns thick, and they are we make them on 35 mm dish with 14 mm viewing area, so they are like really small, and really in our terms it's really thick, but yeah, they're thin gels, like 45 microns thin.
Okay,
Yeah.
because and all right, on those individual gel samples, how many measurements did you make, like in positions? You said you measured different positions on the gel. How many positions?
Around I took images for around like 30 to 50 cells, somewhere in between.
Those were images, but I mean, in terms of like when you're applying a force, I guess the question I'm getting at is, I'm not sure the composition of the gels themselves, but is there a chance that your data is being affected by non-uniform properties in the gel itself? I mean, is it possible that you just, if you were to take different volume elements, that you have different different quantities of polymer chains in them?
Okay, So actually, this gel, it is actually made from two different parts, part A and part B, and changing the ratios of these parts, actually changing the stiffness of the gel. So we have to make sure that we are doing the same ratios for that particular stiffness. So and we did some AFM studies and some geometry studies to make sure that uh, what ratios we are mixing corresponds to that particular stiffness. So after doing all this, we are kind of sure that we have that particular stiffness, and there's no effect of any other thing going on with the cell except for the stiffness.
Okay, all right, because just because you start out with a uniform composition, polymers can actually just diffuse a bit and give you different local compositions, especially over time. So I was just curious, but it sounds like you had done your best to take into account any sort of impact of that. So that's good.
Yeah, we have done several AFM measurements on different locations within the gel, and we kind of take the average of that. There are some local differences, but they are not too much, not
Yeah.
too significant, I'll say.
Yeah, well, that's good. Okay, all right, that's it for me.
Thank you.
Thank you to both our judges. We just have a little extra time. If there was any questions from the audience, you can either type it in right now or speak. I'll give a couple seconds if anybody wants to ask something. In the meantime, I just want to say thank you for everybody coming. This was a great GRC, and a lot of work was put into putting it together. But the reason we do it is for everybody to be able to present and come, and it's always a great event. Also, I just want to invite / remind everybody about the award ceremony tonight. That will be from 5 to 7 p.m. So definitely check that out. I'm not seeing any questions from the chat, and I haven't heard anybody. So I'm just going to call this session and thank both of our presenters, Masood and Nikhil. Those were great talks, and thank you again to both our judges, Dr. Patricia Hayden and Dr. Deborah Charlesworth. We really appreciate your time being able to judge. So yeah, thank you, everybody.
Thank you. It was a wonderful event.
Yeah, absolutely.
Oh, so there's just 2 talks, not 3?
Yeah, just 2 for this one.
Oh, okay, all right.
Yeah.
Thanks very much.
Thank you so much.
See you, everybody.
Thank you.
Yeah.
Bye-bye.